Hello physics students, welcome to the next video. This one we're going to do electric fields, and I've hopefully broken it down into a whole lot of little chunks so that there's a whole lot of little videos rather than one big video. First of all, we're going to do the introduction and we're going to look at Coulomb's law. Now, where would we be without electric fields? There'd be no photocopiers, no faxes, even though faxes are on the way out. It's pretty rare to see a fax these days. No TV, although, again, the TVs that we're now using, the LCD and the plasma TVs, don't really rely as much on electric fields as the old cathode ray tube TVs, but they still do use electric fields. We'd have no lightning, which may or may not be a good thing. No lightning arresters, which would be a good thing. If we didn't have any lightning, we wouldn't need lightning arresters. And no particle filters. And what we mean by particle filters are things like things that filter out smoke and dust. So we couldn't have any clean labs anywhere that do high-level pathology or industrial stuff like making chips and things. We wouldn't have those clean rooms to make that sort of stuff. So electric fields are very important, and right at the end, probably the last couple of videos I will do on electric fields will all be about applications of electric fields. So we've got to do just a quick little bit of revision here about where electric charge comes from and where we get electric fields from. Do we remember the atom? That's the atom. Actually, it's a sporty car. I think it's got the fastest lap time around the Top Gear lap, and that's the Top Gear guy. And I think another model came out and actually still got the fastest lap time around. Pretty cool car, but it's not the atom we're talking about. We're talking about this guy, and we should remember this from physical science. We've got our nucleus with our protons, neutrons, and our electrons orbiting in shells. Lots of different representations of this. Let's have a look at some. Sometimes it looks like this, your more classic symbol. Sometimes this is a representation of the orbitals, so where you would actually see the electrons in an atom. And this is following on from this. And this is the orbitals. If you're doing chemistry, you'll learn about all this, how the electrons don't actually occur in shells, but they occur in orbitals and zones of probability. And these are all some of the orbitals that you have, different shapes, which are basically zones of probability where the electrons may occur. But we still think of shells, and even when we do atomic physics, we do think of energy levels, and we're trying to represent something that we can't see with the human eye. So it's always a compromise, these diagrams, but there's a reason why they're designed that way. And in reality, even our representation there is incorrect, because we should, hopefully, if we've done a bit of science reading in our lives, recognize that the nucleus is much more complicated than just protons and neutrons, because the protons and neutrons are made up of quarks, different types of quarks. And so, whereas the electron is pretty much still believed to be a fundamental particle, protons and neutrons aren't fundamental particles because they've been split apart into up and down quarks and various other things as well. So what we tell you is a lot simpler than the real world, because we're only learning physics. And this little sentence here is important. So what we're saying here is if the protons and neutrons in this picture were 10 centimeters across, so 10 centimeters across there, then the quarks and electrons would be 0.1 of a millimeter if everything was drawn to scale in size, and the entire atom from there to there would be 10 kilometers across. So this is a representation of something that's significantly bigger, but a lot of nothing. And so that's my point. Atoms are mostly empty space. We're made up of atoms, and we're mostly empty space. Protons and neutrons occur in the nucleus. The nucleus is small but dense and tightly held together. Protons have positive charge, neutrons have negative charge. We don't need to know about quarks in our stuff. Electrons are negative and very little mass, and the electrons occur in the outer shell and loosely bound. So that's a recap of everything we learnt in physical science. Now at this point I would demonstrate the Van de Graaff generator and play with some balloons, and we'll do that in class once we start this. So that's just a little reminder for me to do it. Now what about Van de Graaff generators? Well, this is our Van de Graaff generator. So here's a representation of a Van de Graaff generator. We have one like this, but we don't have the secondary charge. And how it works is there's a big rubber band, and there's a motor and a roller, and this bottom part of the Van de Graaff generator is earthed, and then the rubber band goes up. This cylinder is insulated, so we have a large metal sphere up here, and because this metal sphere is insulated from the earth by, in our case we've got a Bakelite rod, but usually it's just plastic, the roller goes up here and the rubber goes up here and goes across another roller. And what's happening is that the rubber holds some electrons very weakly, and when it goes up here it goes through a very tight circle, so circular motion, and the electrostatic attraction of the electrons to the rubber is not sufficient, or doesn't provide, if we want to talk physics, enough centripetal force to make the electrons go around, so they're actually flung off onto this collector. And because the electrons are flung off, they gather up here on this metal dome and position themselves all around evenly, and then the rubber band comes down deficient in electrons, so positively charged, and so all the electrons that are in the earth coming through here, some electrons jump on because they're actually attracted to the positiveness of the rubber, and so this is effectively neutral up here, and this is positive up here. And you can read this, pause this and read all that, and it explains it in some words that have bigger syllables, if you like. Alright, so that's how ours works, and we'll demonstrate that in class. Now, searching for that picture, I found this one. This one is a Van de Graaff generator, but whoever drew this one didn't know much about physics, I tend to think, because here we've got the positive charge, protons, actually being generated up here. The only way that this could be positive is if electrons are actually being flung into the earth, and so that's being left positive, and that's just not what's happening. So it's just a warning, whenever you're looking for stuff on the internet, it's not always correct. You can, however, make your own if you want to experiment and see if I'm actually right about it being negative, and it would look something like that. You can go on the web and type into Google, and this one's sponsored by Foster's, has a little motor there and a rubber band, and apparently it works quite well, not too hard to make, so if you want to, you can. However, with Van de Graaff generators, bigger is better, and Van de Graaff generators were invented so that people could study static electricity, because there wasn't much known about it, and it was a way of generating large electric fields as well. So if you can make a electric field and look at static electricity with a Van de Graaff generator on the desk, how about making one that's as big as a shed? And these are quite big. These were made by MIT, I think, in America, in a shed. I think I've got another picture here. You can see how big they are. There's a standard sized person. There they are, slightly sharper picture. And so these are large Van de Graaff generators, and I've got a picture of them being used, generating large sparks, and people could investigate static electricity and electric fields. There's some people protected by what's called a Faraday cage, and we'll be looking at Faraday cages in another video as well. Pretty impressive. Now there's a couple of videos on your OneNote. One's a big spark, where you can see some videos of very big sparks, and also a Van de Graaff generator that's probably being used in some science exhibits and stuff being demonstrated in someone's backyard, which is quite impressive as well. So go onto OneNote and have a look at those. Now Coulomb's law, this was Coulomb, and he was around in the late 18th century. He used what's a very sensitive electrostatic torsion bar balance. Now we've seen a torsion bar balance before when Cavendish was using it to work out the universal gravitational constant. Now this will look somewhat similar, but be slightly different, because instead of looking at gravity, Coulomb was looking at electrostatic charges and the force between charges. So this is what his experiment looked like. There's the rods and the pivot, and there's the little torsion and the dial and everything, and there's another dome that was put in there to make, like this, a charge was put on there and a charge was put on there, and then you could measure the force between those charges. And here's a modern day one which is a little bit clearer. You can put this charge on there, that's insulated, put a charge on there, and then there's the torsion section, and you can measure the force through a complicated process of calibrating and experimenting. Quite fiddly sort of experiment. You have to devote a lot of time and effort to get it right. Anyway, Coulomb was able to find that the magnitude of the force was proportional to the product of the charges, which was interesting. The magnitude of the force was inversely proportional to the square of the distance separating the charges. That's a mouthful. The direction of the force was along a line joining the centers of the charges, and he put it into an equation, and this is the equation that these words describe. So you got F equals K Q1 Q2 on D squared. Click this, and this is what the textbook has, and this is what our formula has. So we would say force electric field equals, now K is a constant. It's called the electrostatic constant, hence the E, and it has a value of 9 times by 10 to the 9 Newton meters squared coulombs to the minus 2. Again, these units are here just to make sure that when we put meters into there and coulombs into there, we get newtons out of here. Okay, and there's our charges. So here's this diagram. Q1 is a charge represented by a point. Can be a sphere, but we still represent it as a point, much like we did with gravity and mass. And Q2 and D, or R in this case, not the radius, but is this distance between those point charges, and each of them will experience an equal but opposite force. And in this case, because it's a positive charge and a negative charge, it's the force of attraction. If these were both positive, they'd be repelling each other. If they were both negative, they'd be repelling each other. So in electrostatics, like charges repel, unlike charges attract. And remember that this is a vector quantity, so you need to give a direction, like shown here. So you should now be able to do some questions relating to Coulomb's law, simple application of it. So these are the questions where you basically have to find the stuff to put into Faraday's law. F equals K Q1 Q2 on R squared. So have a go at those, and in the next video we'll be looking at how we actually represent electric fields. Cheerio!